Hello everybody, today I'm going to introduce a data structure called a min heap and two of its key operations, insert and pop. So what exactly is a min heap? A min heap is a data structure that can help us easily access the smallest value given a large set of values. This is possible because a min heap is a complete binary tree. And the binary aspect means that every single node is going to have at most 2 children. It can have less, as you can see here, 10 has no children at all. And the complete aspect means that every single level of our tree is going to be completely filled except possibly the very last layer, only under the exception that it's filled in from left to right. This structure gives us a max depth for this tree of log n. And the key characteristic of a min heap is that the root is going to be the smallest value. Every single node is going to be smaller than or equal to its children. No value is going to be larger than either of its children. So from top to bottom, smaller values are on top, larger values are on the bottom. Now, how do we represent this? Min heaps are commonly represented using arrays, and just to simplify calculations a little bit, I'm going to initialize the index 0 to be some random dummy placeholder. And the root is going to be at index 1. And as you can see in this array, the order is just the order of our min heap tree from top to bottom, left to right, 7, 9, 8, 7, 9, 8, 11, 15, 12, 10, 11, 15, 12, 10. And if we have a node or a value at index I, then its left child is going to have an index of 2i. Its right child is going to have an index of 2i plus 1. And finally, its parent is going to have an index of the floor of I divided by 2. Now remember, every single node is going to be smaller than or equal to its children, so that means a value at index I is going to be less than or equal to a value at index 2i plus 1. This is its right child, and if I is also going to be less than or equal to a of 2i. This is its right child. Now, let's move on to the insert operation. The purpose of this operation is just to add in a new value to our data structure, but we have to maintain the min heap properties. How do we do this? We're going to add in the newly added value to the very bottom of our tree. Remember, they're added from left to right, so we're going to put it in the leftmost available position. So we put it here. We're going to compare it with its parent. If it's smaller than its parent, we're going to swap it. We're going to keep doing this until either this node becomes the root or it's larger than its parent. So let's do an example. Say I want to insert 6. Put 6 at the very bottom where we have an available spot. We're going to compare 6 with 10. 10 is larger than 6, so we swap it. 6 is smaller than 8, we swap it. 6 is smaller than 7, swap it once again. As you can see, every single node is going to be smaller than both of its children, and also this has the properties of a complete binary tree. Now, let's move on to the pop operation. The pop operation is just to extract the smallest value within our min heap data structure. And we already know that the smallest value is located at the root. So how do we do this? We're just going to output the root value, delete the root, and we're going to take our last value in our min heap, which is located at the end of the array or at the very bottom layer, the rightmost value. We're going to take this value, put it in the location of where the root used to be, and we're going to compare it with its children. If it's larger than its children, we're going to swap it with the smallest value of smallest child. I'm going to keep doing this until we get back the min heap property. So we output 7, delete this node. I'm going to put 14 where 7 used to be at the root. 14 is larger than both 9 and 8, but we're going to swap it with 8 because 8 is a smaller child. Now, 14 is still larger than both 12 and 10, and we're going to swap it with 10 because 10 is a smaller child. And as you can see here, we have a min heap. We outputted the smallest value before we deleted it, and every single node is smaller than both of its children, and we do still have a complete binary tree. And each operation, pop and insert, has a runtime of O of log n. That's it for the quick introduction to min heaps. Thank you for listening.